Okay, welcome everybody to this course in system simulation. So my name is Reidar Kristoffersen. I'm going then to guide you through this very challenging and interesting course called system simulation, which in short is to simulate any system. Any system. We don't care what kind of problem it is, as long as it is something that we can model, program, simulate. That's what we like. I don't have the computer online, but you'll find now on the home page on this learning a little bit material and also little general information about the course. So I can quickly repeat it here. We have been given this room, which is not the best. According to his learning, you should be roughly 100, and there should be 70 seats or something in this room, so it's a little small. So hopefully a lot of you is going to bail out. No, I don't want to take this stupid course. So I'll give some terrible lectures in the beginning just to get the number down. I think you have a deadline until the 15th of September, then you can choose which course you actually are going to take. So it's quite common, actually. We have 2 more seats in front, if you can navigate your way. And I have 1 more chair and 1 more chair here. So please find the seats. So these lists that we have on this learning, they are just preliminary, internal anyway, so it really doesn't matter. If you are on the list or not, you are not devoted to taking the course either way. So remember, it's learning, it's just internal. So I'm going to use its learning as the portal for information, for exercises, for everything. So you have to have access on his learning. If you don't have access to his learning, tell me. Then I'll have to edit you in somehow. Just give me, talk to me during the breaks, then I can get your name and add you on his learning. The weekly schedule, we have lectures today, and I think I have to use the Tuesday lectures from 18 to 20 as lecture time. I know it's very late, so you're all going to fall asleep, but I mean, you're asleep anyway, so who cares? So Tuesdays and Wednesdays, there will be lecture hours, 4 lectures each week. Then it's the question of the exercises, and for now we will start using Friday for guidance for the exercises. Friday from 2 to 4 in room F2. That's what we have been given so far. Mondays 18 to 20, I think we will skip, at least for now. Maybe we can use them later if there is a desire among you to use them anyway, but for now we skip the Monday lectures. I'll see if I can arrange some bigger rooms. This one is a little bit crowded, but I think it should be okay if necessary. That was roughly the weekly schedule. A little bit about the course, what we are talking about, what kind of systems, what kind of problems, what kind of previous courses should you have taken before you are daring to enter this room. Well, a problem, typical engineering problem, that you will encounter in this course might be something like this. You have wind hitting a turbine, generating electricity, electric power, into a pump system that then pumps water into a storage tank above your little house. And say now you have some excess energy, then you can start heating up the water. And then the question is, how long can you take a shower? So typically we mix a lot of things into one and the same problem. So here we're going to need some relation wind speed, given the wind speed as an input, how much power can we get right here over time. This will of course change. This wind speed will change according to the local weather. Then the pump system, of course, from electricity to fluid motion, maybe resistance in the fluid pipelines, heating of water, well, that's not so difficult. Okay, here resistance in the water system, the shower system, how that one should be designed, and so on and so forth. So we have a lot of modeling to do here, finding also the correct equations that can describe such a system, and then put it all together in one single program and solve everything with respect to time. We have a simulation. And then maybe afterwards we are not too happy with the results. Okay, then we might have to go back, change some of the parameters, having a better propeller, bigger blades or something, so we can get more energy. I want to take a longer shower. Problems like that. Then we are talking about optimization. So the course, this course will then cover these types of problems. It was recognized actually many years ago when we got students into the project and master classes that they really had problems handling how to handle complex mixed problems. So this was sort of an attempt to remedy that. Also, you will get programming training here. And the programming language is MATLAB. MATLAB only. Which of course all know MATLAB very well. So that's good. Right. How I was expecting. Yay! Does anybody here have never touched MATLAB? Never touched MATLAB. Anybody has used MATLAB less than 10 hours? 20 hours? 50 hours? Okay, thank you. So, at least most of you have a little bit idea what's going on. You should not be afraid of the programming part in this course. If you haven't programmed much, then the first exercise will be deadly. The next one then will be very easy, and the rest will be very easy. So as soon as you can get things started, you will get the hang of it very easy. So the programming part is not difficult. You can of course take it fairly long if you want cosmetically beautiful printout in the graphs, the figures, animations. Then you can spend hours and hours programming if you want, but you don't have to. The logic, the important part, is done fairly easy. Roughly planned for the semester, we have week number 35, 36, 35, that's this week. Yeah, please enter. I don't know if there are any free chairs. One there, maybe. No. Well, yeah, we have some chairs. Yeah, excellent. Good. Week 35. That is today, actually, and then next week. A little bit intro, and then MATLAB. Just a crash course for those of you who felt a little bit uneasy with MATLAB. So that will be included in the introduction. Take some MATLAB examples. And then we will have chapter 2, which is then source load. The material is stolen from different textbooks. So I don't have one single textbook for you. There exists, most of what I've stolen is taken from one very big book, and it's terrible and it's very expensive, so don't buy it. Instead, you'll find PDF files on this learning. It's not legal, but don't tell anybody, or else I'll get in trouble. So the chapter 1, introduction, we will cover today. That's taken from another book called, what was it, Brown or something? Oh, Burton. While chapter 2, 3, 5, and the rest is taken from a book by a guy called Brown. So yes, it's possible to find these books, but don't buy them. They're too expensive. From week 37 to week 40, we are talking about bond graph. What is bond graph? In the process of describing such a problem, modeling it, finding all the equations, and then setting the equations together in one single computer program, that is sort of tricky. Bond graph is a tool, graphical tool, that helps us with just that part of the process. Going from a mathematical model, a whole bunch of equations, joining them together, and then identifying the only necessary equations needed to describe the entire system, what we call the state equations. So bond graph is a graphical tool which we are going to deal with a lot. So you don't have to use it if you want to do all the algebra yourself, be my guest. But bond graph is fairly strong tool if you know how to use it. Then week 41, we are talking about optimization. The process of having a desired results. I really want to take a long shower. How to do that? How to change the parameters, how to change the input so I get the desired result. So then you have to optimize the entire problem. So this is only, we just touch this area. It's actually a very huge topic by itself. So we are just peeking into it. Only 1 week. Then we will have a little bit of regulation and control. Regulation, control. Then we are touching into another topic from the cybernetics. I guess some of you have had this cybernetic course, some of you haven't. So we are not going to touch too much or overlap too much with it. But you should know a little bit about regulation and control, even in this course, a little bit about PID controllers, feedback loops, stuff like that. How to control a process. Then the rest of the semester we will have a project. And for this project you will form groups. The ideal group number will be say 4 students. You will then find your own project. You can design it whatever you want, with discussion with me, of course. So typically the students are way too ambitious, so they have a very complex problem. It's impossible to solve. They start there. That's a bad idea. So my job is sort of push you down. Start simple and then make it work, and then expand it if possible. From this project, you will then write a report. You will produce a poster, and then we will have a poster session. You will have to defend your poster. Sounds very scary, but actually it's going to be the nicest oral exam you'll ever have. You're just standing there drinking coffee and chatting with people walking by. That's it. for 2 hours. Very easy oral exam, I can promise you. Now this, according to the law, will count for 30% of the entire score. And then we will have an exam on the 2nd of December, which then should be 70%. I'm not allowed to weight any more than 30% of works during the semester. So this is the law. In practice, this one quite rapidly jumps up to 50%. So I'll do that without telling anybody. I think that's for your benefit. So the written exam is rather boring. That's something we have to go through. So that's the weekly schedule. There will be exercises, written exercises. We don't have any inbox, outbox. We will use It's Learning, so you upload your answers electronically. We will have then a couple of student assistants that corrects them, also give you some guidance. Also, we have a scientific assistant, Alexander, show your face, yeah. So you know how he looks. So he will also be around helping with exercises, and also can answer your questions if you have some nasty problems that the student assistants can't answer. Also, as you can see today, he's our cameraman. So I plan to stream the lectures, put them out on YouTube. That's normally quite popular. People who's not here, or yeah, whatever, if you're sick, have to go away sometime, then you can find the lectures on YouTube. We hope the camera is good enough so you can read the blackboard, so you can read the screen, and also hear my voice. We are currently looking for a better camera, so hopefully it will be even better. I assume everybody here has a private laptop. Does anybody who doesn't have a laptop? If you don't, then steal one, whatever. You have to use a laptop. And you have to install MATLAB on the laptop, of course. MATLAB is a very good program, and you get it for free here on the university. So definitely something I will recommend. Be careful though with MATLAB. It's very expensive if you go to the industry. Then you're in trouble. If you on your first day in your new job, you go to the boss and bang your fist into his desk and say, I want MATLAB. Then he throws you out because it's very expensive. Now there exists free versions of something similar called Octave, which you can download for free. So we should actually have shown you that one as well. Maybe we can have time to do that later on. Okay, that should be the administrative information, at least for now. Any questions from you? That's okay. The first exercise, that is going to be a pure programming exercise, just MATLAB. So the first exercise, I want everybody to do that individually. So that will be a mandatory exercise. I want to ensure everybody is up and running on MATLAB. So that's a minimum that is required from you. The rest of the exercises, there you should form groups and work together in groups. 4 students, that's what I say is a very good group. So of course you can still hand them in individually if you want, but student groups, that is very good to start form early, since you are going to do a project here anyway at the end of the semester. When this presentation is going to take place? I don't know. I would guess at least for before the exam, maybe during this buffer week that we have after the last exercise, before the last lecture, and then before the first exam. There should be a week there. But that's something that we can discuss later on. Okay, then I don't have any more administrative things. No questions from you? Everything is clear? Okay. As I said, I have stolen some chapters from different books, and this introduction is taken then from a book by a guy called Burton. It's a little in sort of a general language, some general definitions that we have to be clear on, so that we know what we are talking about. So I'll start just quickly today going through this chapter 1. And hopefully also we will have some time to do an example. Introduction. When we talk about a system, you should think in terms of a control volume, like you had in the basic fluid mechanical course. We sort of isolate a problem, a system, with some physical or logical boundaries. So here you have a control surface, control volume, and then you talk to the rest of the surroundings through a port. And your surroundings here, that is the rest of the universe. So you isolate your problem and just see how this system talks to the rest of the world. Sometimes you don't have a port. It's isolated. So you have no exchange of information or energy or anything into your surroundings. That's quite okay. But you may or may not have one or even many ports to the rest of the universe. So different types of systems that we are going to look into. We have mechanical. That's Newton's law of motions. Here we are talking motion back and forth, straight line, also rotational problems. So this is, here you need basic mechanics. Then we are talking about fluid systems. So basic fluid mechanics, yes, something that you need. We are talking about electric system. Basic electrics, Kirchhoff's laws, stuff like that you should know. But nothing complex, but a little bit electricity you should be familiar with. Thermal systems, well, not as much. We are going to touch the problem, address it, but we are not going into thermodynamical systems. No, that is a topic of its own. So a little bit thermal problems. And then other problems. We have biological we have economical, you have whatever you want systems. Whenever you have something changing with time, according to one or more laws, constitutional equations, you can form a system and we can try to analyze it and simulate it. But of course, this is the basics, the most important part for us, yes. And then, as you saw, how to attack a problem when we have mixed it all together in one single problem. That's so frequently when people run into problems. So we are mixing it up. You have static systems versus dynamic. Static systems, time independent. And dynamic, time dependent. Things are changing with time. Of course, a dynamic system may have a static state, which may or may not be stable. So he can sort of pause, and then nothing seems to be changing for a long, long time, and all of a sudden he starts to move again. That can happen. So dynamical systems may be static sometimes. Also, we have chaotic systems. Chaotic systems, well, they are typically time dependent. And anybody has touched any chaotic systems? You know the definition for chaos? It is extremely or sort of infinitely dependent on the input parameters, the input values. What should we call it? Chaotic, time dependent, and extremely, or just sensitive then. Sensitive to the initial conditions. So chaos, that's something we might encounter in this course. So last year we had a group, they were looking into the problems with a water wheel. So you have an axis, several arms, and then at the end of each arm you have a water bucket, like this. And then you let water fall. And then you start to rotate this system. So when a bucket passes this, this water stream, he gets a little bit of water inside the bucket. Then in each bucket you make a hole. So then he's heavy initially, but then the water falls out and he becomes lighter and lighter. And then something chaotic will happen here. He starts to move. When this one is heavy, becomes light on this side, gets some more water, gets heavy again, and so on. And then one might guess that yes, this will just go on forever, as long as you put water in. But then not necessarily. All of a sudden he can stop and then go the other way. And then, well, it's impossible to predict it correctly. So you can simulate it and get one solution. Then you can simulate again using a little bit higher accuracy. You get a totally different answer. You simulate the third time, even more accurate, and you get a totally different solution again. You will always end up with a new solution, no matter what you do. Very sensitive to the initial data. So chaos might be something that you will encounter. This is not going to be a course in either mechanical, fluid, electric, thermal. You should know this already. So I'm not going to teach you anything further than what you already should know. Also, it should not be a course in numerical methods. Yes, we are going to solve a lot of ordinary differential equations numerically, but it's not really our job how they are solved and how accurately they are solved. Still, a little bit unavoidable that you have to know a little bit about numerical methods, but it's not going to be much. Here you will have this figure 1-1 in this chapter 1 from Burton. Sort of describes the entire process with system simulation or system analysis or whatever you want to call it. In several universities you will have a lot of these system simulation like courses. So some universities they don't teach mechanical, fluid, electric. They don't teach any of these basic courses at all. They have system simulation 1, 2, 3, 4. They always mix it together, and then they teach the students the basic things as it will be needed in all the different system courses. That's another way to do it. So here, just a quick description of what we are talking about, system simulation or system analysis or whatever. A physical phenomenon, device, a system that should be studied, that we want to check. And then we are talking about objective. What are we actually seeking here? What do we want to know about this system? What do we desire? And also there, how well should we look into the problem? Like this example, you have wind hitting a turbine blade. So this turbine starts to rotate. Now that is a nasty problem by itself. In detail here you are talking fluid motion around a wing profile which are in motion. This is not funny. You have to solve the Navier-Stokes equations. You are talking partial differential equations. Very hard problem. This is not for us. So we say skip this. That's too advanced for us. We don't have time for this. So we are seeking very crude simplifications here. We have to sort of go down on the level of sophistication here to be able to solve the coupled problems more easily. So what we want here typically will then be, yeah, it could be something, a torque in Newton meters on this axis as a function of, say, wind speed in meters per second. So if we have such a relation, some formula here saying alpha v to the power of 3 or something, then we are happy. Then we have modeled this very easy, maybe a little bit too crude, but at least we can get things started, fairly straight on. So this way too advanced. So no partial differential equation should be needed in this course. We have to model it down to something that we easily can solve. Goes also with the next steps here, finding simplifications, assumptions that makes life easy, so we have a problem we can actually solve. Idealized physical systems. So then we need some constitutive equations like Hooke's law, Ohm's law, ideal gas law, and stuff like that, to make everything connected. And then, of course, the physical laws like Newton's law of motion, Bernoulli, whatever we need to mix everything together to describe then a mathematical, or to obtain a mathematical model. And here we then have to do some algebra to narrow the equations down to a simple system required to describe the behavior that we are interested in. So here, of course, this modeling, coupling all the equations down to a simple mathematical model, that is the bond graph part. We can do this for us. So here we will end up with a very neat, compact set of first-order ordinary differential equations that can easily be solved numerically. Analytically, that's for babies. That demands a linear problem. Our problems, they are never going to be linear. They're going to be very nasty. They're going sometimes to be chaotic. You can't describe this with analytical solutions. So the analytical part here you can almost forget. You don't get it. You have to do it numerically. Sometimes, of course, we will be able to find an analytical solution just for comparison, but in general, no, just forget the analytical part. We have to solve it numerically. And then, when we have then a solution, then we can start to look into the solution here. Are we happy with it? Do we have some experimental results that we can compare with to see that, yes, we have captured the physics, it behaves as it should? Or do we get some very crazy results? Meaning we have to go back here and maybe increase the level of sophistication here. Maybe this one wasn't good enough, so maybe we need to expand this one a little bit. I don't know, play around with different models so that we can get a better behavior. Or you think in terms of optimization. Yes, we get a result, but we don't like it, so we have to change some parameters to get a better result. Then we have to do this loop many, many times. So that is bond graph for you. Okay. So bond graph is this part. That is the bond graph part. And then numerical, a little bit programming in MATLAB. And then the optimization, well, that is a loop around the entire problem. We'll come back to that later on. Okay, any questions? Now, if any of you haven't access to eLearning, tell me now during the break, so I have your name and then I can try to add you. Okay, we take a break.